Okay, let's dive into this. Today, we're unpacking a truly groundbreaking 2026 paper. It's called Rendering Coherent Scattering via Quantum Collision Models. This work comes to us from an absolutely brilliant team of researchers: João Sos Ferreira, Spencer S. Topple, Pierre Fromholtz, and James R. Wooten. And listen, what they've put together here, it isn't just some minor incremental update to how we generate computer graphics. No, this is a fundamental reimagining of how light and matter actually interact in a digital space. We're going to unpack exactly how they're using actual quantum mechanics to solve a problem that has secretly been holding back the visual effects industry for years.
So have you ever been watching a massive, high-budget movie or maybe playing a beautifully rendered video game, and you notice that certain materials just react unnaturally to complex lighting? Think about a translucent crystal or maybe a multi-layered metallic surface. It just looks a bit too flat, right? A little too lifeless under intense light. You can't quite put your finger on it, but your brain just instantly knows, yep, that's CGI. Well, that uncanny valley of lighting is the hidden flaw in current visual effects. So why does traditional light rendering break down in these complex environments? The answer actually lies in the deeply held assumptions baked right into the software we use to build these digital worlds.
Here's our roadmap for this explainer. We'll start with the limits of current CGI, then enter quantum collision models, look at how light actually meets matter, discuss pre-computing with quantum tech, and finally, look ahead at the future of virtual materials.
All right, Section 1, the limits of current CGI. Let's look at the actual problem here.
Now, what's really interesting about this slide is the sharp contrast between what our software assumes and what reality actually does. You see, for decades, the absolute gold standard in rendering has been classical ray tracing. And hey, it's a fantastic tool, but it has this invisible ceiling, because it's entirely based on how we tell the computer to interpret a surface. Traditional rendering fundamentally assumes that the optical properties of a material are static. Basically, it assumes the object just sits there, completely unchanged by the light hitting it. But dynamic reality tells a completely different story. In the physical world, optical properties often evolve in response to incident illumination. When light hits a complex material, it can temporarily change how that material behaves. The material doesn't just passively bounce light, it actively reacts.
And that brings us to the core failure. Traditional rendering completely fails when material properties dynamically evolve. I mean, think about it. If a beam of light hits a surface and actually alters the energetic state or the optical behavior of that surface, classic ray tracing simply doesn't have the math to comprehend what happens to the next beam of light that hits it. It literally just treats every single ray of light like it's hitting a static, unchanging brick wall. Which brings us to Section 2. Enter quantum collision models. This is where we see a truly radical paradigm shift.
So, what exactly is a quantum collision model? By definition, it's a shading framework that treats incident light and material excitations as quantized modes interacting dynamically. Okay, if that sounds like intense scientific jargon, which, let's be honest, it kind of is, just think of it like a microscopic, highly ordered game of quantum pinball. Instead of a continuous, simple beam of light bouncing off a flat surface, the light and the matter are broken down into discrete interactive packets, or quantized modes. When the light hits the material, they collide, they exchange energy, and they dynamically change each other in real time. But here is the brilliant part right from the paper itself. It proposes a novel shading framework that combines classical ray tracing with a quantum collision model. I really want to emphasize this because the authors aren't throwing away classic ray tracing. I mean, ray tracing is still incredibly efficient for getting light from a source across a room and onto an object. What they're doing is supercharging it. They use classical ray tracing for the macro scale, and then they seamlessly weave in this new quantum layer for the micro scale right at that exact moment where the light physically meets the complex material.
Moving on to Section 3, how light meets matter. Let's lift the hood and look at the actual mechanics here.
So how do you mathematically simulate this quantum pinball game? Well, the process happens in 3 main steps. Step 1, as we mentioned, you treat both the light and the matter as quantized modes, they're active participants. Step 2, you model the subsurface scattering as unitary collisions. Subsurface scattering is basically what happens when light penetrates something like skin or wax, bounces around inside, and then comes back out. This framework models those internal bounces as symmetry-constrained unitary collisions, which is really just a fancy way of saying energy and probability are strictly preserved, just like in actual quantum physics. And finally, Step 3. Because of this rigorous mathematical modeling, the system naturally captures chaotic multi-layer interference.
And this brilliantly illustrates why this method is so revolutionary.
By using this quantum framework, the renderer finally unlocks non-integrable dynamics and chaotic optical responses. It actually embraces the beautiful, messy, chaotic physics of real-world multilayer interference that older, simplified models actively had to ignore. The light isn't just bouncing anymore. Its waves are interfering with each other inside the material in complex, totally unpredictable ways, which yields optical effects that look astonishingly real.
Let's bring this back down to Earth in Section 4, Pre-computing with Quantum Tech, a highly practical workaround.
Now you might be wondering, this sounds computationally impossible. Like, how could a standard workstation computer, let alone a gaming console, possibly handle all this chaotic quantum data in real time? Well, the researchers solved this with an incredibly elegant, practical workaround. First, they pre-compute the collision operators, so the heavy lifting isn't actually done live while you're playing a game or rendering a scene. Second, they use near-term quantum computers to do that incredibly complex pre-computation. And third, they take the output of those quantum computers and use it to generate standard BSDFs.
For those of you who might not be deep in the weeds of 3D modeling, let's clearly define a BSDF, or bidirectional scattering distribution function. Basically, you can think of it as the standard blueprint file that tells a rendering engine exactly how light scatters off a material. Literally, every piece of 3D software uses them. So the absolute genius here is that this mind-bending dynamic quantum math is executed in a lab on a quantum computer, but the result is seamlessly packaged into a standard BSDF format that today's existing CGI software can actually read and utilize perfectly.
And that leads us to our final part, Section 5, the future of virtual materials. Let's look at the final output. We've talked a lot about the math. So let's connect this intense quantum framework directly to the visual output that you and I will actually see on our screens. The ultimate result of this pipeline is the creation of physics-inspired materials with distinct optical signatures. This isn't just some theoretical exercise, you guys. It's about giving digital artists the power to create hyper-realistic materials that have literally never existed in a digital space before. We're talking about materials that shift, shimmer, and react to light with the exact chaotic beauty of the natural world, all because they're fundamentally driven by the real rules of physics.
So the crucial point is, this entire journey we've just mapped out, we start by overcoming the rigid static property limits of traditional CGI. We achieve that by using quantum collision models to accurately handle complex subsurface scattering. We make it completely usable by outputting standard BSDF files via near-term quantum computing. And the final product? A digital world populated with materials that have distinct, beautifully accurate optical signatures. It's just an incredibly elegant solution from start to finish. Which leaves us with this final provocative thought. Right now, this team has successfully mapped coherent scattering and dynamic light interactions into a file your computer can read today. But as quantum computing inevitably advances, getting faster and way more capable, what impossible materials will we render next? When the fundamental physics of the universe can be perfectly simulated and packaged for our screens, the boundary between digital rendering and reality might just disappear entirely. Thank you for joining me for this explainer, and I'll catch you in the next one.